looks happy again. Use the graph of y equals 2 to the x to sketch the graph of 3 times 2 to the negative x plus 2. We are going to review our very first unit. Hopefully by now you're feeling quite confident in your transformations. So what's always going to happen is you're going to think of your parent graph. So your parent graph always has 0, 1 and 1, 2. In fact, 2 points is enough with the asymptote to draw this accurately. Now, we want to graph y equals 3 bracket 2 to the negative x plus 2. A couple of things from transformations that we have to remember. Okay? We have to remember what's vertical, what's horizontal. We have to remember that when we have a horizontal reflection along with a horizontal translation, that we always have to write it in factored form first. Right? That was something that we forgot in that first unit often. It's going to come up again. So before I do anything, I am going to rewrite this, and I'm going to factor out that negative to be negative x minus 2. The next thing I'm going to do, and this is one of the reasons we didn't do this in the first unit, is you have to recognize that your parent graph is the 2 to the x graph. Okay? And this is different than the functions that we had in the first unit, because in the first unit, none of our functions had like big numbers in them. Like my parent graph has a big 2. This 2 and this x are part of my parent graph. And there are some very common mistakes that students make now that you have a big 2 in the question. Mistake number 1. You see 3 times 2. Oh my goodness, is that tempting. You feel like, I'm good at mental math. I know that 3 times 2 is 6. I'm going to show off my mental math skills and write a 6 right away. Well, that's good that you're good at mental math, but you are not following order of operations. BEDMAS is very important. They teach it to you already in middle school. And in BEDMAS, there's brackets, then E is exponents. You have to do exponents before you multiply or divide. This is an exponent. So before I can multiply the 3 times 2, I have to deal with that exponent. That exponent has an x. I can't actually deal with it. So I'm not allowed to multiply the 3 times 2. Oh, but you guys will be tempted. You will see that 3 times 2 right out in front, and you'll be just like, I'm going to do it. I'm going to write a 6. And then it's going to go bad from there. So, first thing, we can't multiply that 3 times 2. Second, I put a green box around the 2 and the x because when I'm going from left to right, and you know how we used to label things? This is going to be a vertical stretch. You're going to multiply your y values by 3. You skip over the 2 because the 2 is part of your parent graph. The next thing that we run into is that negative. That's a horizontal reflection. You're going to multiply your x values by negative 1. And finally, the minus 2 is a horizontal translation. It's in the exponent where the x is. So anything in the exponent where the x is going to be horizontal. That's a horizontal translation. And we are, just like we always know, that minus 2 means we're moving it 2 to the right. Now, when we did graphing with sine and cosine, we learned DABC, which was a shortcut. For exponential functions, we go back to chapter 1 and do it exactly the same way we did our transformations all along. How did we do our transformations all along? Well, we took key points, and in this case, we're also going to look at what happens to our asymptote. So what are our 2 key points? There's 0, 1, and 1, 2. And we always did our stretches and compressions first, then we did our translations afterwards. So What kind of stretches and compressions do we have? We have to multiply our x values by -1 and our y values by 3. The only translation we have is 2 to the right. So what happens? I'm going to get 0, 3 and -1, 6. Moving 2 to the right, this is now 2, 3, and this one is now 1, 6. We are also going to look at our asymptote and see where it goes. Now the nice thing about the asymptote is it starts at 0. So no multiplying will ever affect a 0. Multiply by whatever number you want, 0 will still be 0. The only way you are going to affect a horizontal asymptote is if you translate it either up or down. Can you see that taking this dotted line, that's infinite, and moving it to the right, it's going to be basically in the same spot. So our horizontal asymptote stays at x equals 0. I'm going to draw a new graph. I'm going to label my asymptote, not x equals 0. You guys are supposed to say something when I do typos. There we go. It stays at y equals 2. That's what happened. I didn't label it on my regular graph, and then I make a mental math mistake. So if we take our time, label things well, chances are we'll make less mental math mistakes. I'm going to start by labeling my asymptote. It didn't change because we didn't move things up or down. I'm going to go to my points. I've got 2, 3. Two, 3, and I've got 1, 6. Once you have 2 points, it's going to be decreasing. Go towards your asymptote, put an arrowhead on the end, have the shape of your exponential graph still there. This is our final graph. So we are revisiting our transformations unit and doing it again. Yeah. Now we're going to do a couple more. Do you have space to do another graph on page 346? So on page 346, we're going to practice another graph. We're going to graph y equals -5 times 3. I'll put it in factor form already for you. Let's graph this. So if you get a question like this, part 1 is you have to recognize what's the parent graph. The parent graph is y equals, the base is 3. I'm going to put a box around that base. Here is my parent graph, 3 to the x. Don't be tempted to multiply that 5 by that 3, because that has an exponent. We have to follow order of operations. And so, quickly off to the side, I draw 3 to the x. It has 0, 1, 1, 3. It has an asymptote at y equals 0. And is an increasing exponential function. If I'm labeling here, this is going to be a vertical reflection, this is a vertical stretch. Both of those can be done at the same time. We're going to multiply our y values by a -5. Moving from left to right, the next thing we run into is this 2. That is a horizontal compression. Remember that a 2 inside with the x multiplies the x values by the reciprocal. We're going to multiply our x values by 1/2. The +4 horizontal translation, 4 to the left. And the minus 7 is a vertical translation, 7 down. Again, lots of things are happening here. We're going to take our original points of 0, 1 and 1, 3. We're also going to take our original asymptote at y equals 0 and see what happens. Set up, we do our stretches and compressions first, followed by our translations. Do we have stretches and compressions? Yes, we're going to multiply x by a half and y by negative 5. And then we're going to go 4 to the left and 7 down. And now it's just a matter of doing the mental math. X by half, this stays 0. Y by negative 5, that becomes negative 5. This becomes 1 half, and y by negative 5, negative 15. Four to the left, negative 4, 7 down, negative 12. 4 to the left, negative 3.5, 7 down, negative 22. What's going to happen to our asymptote? Only thing that's going to affect it is if you move up or down. We are moving 7 down, so it's going to go to y equals negative 7. So with those 2 points and your asymptote, you can draw a very accurate graph. Y equals negative 7. And you notice that as I'm thinking about this, like look how tiny I made my scale on my y-axis. Why did I do that? Because I knew that I'd have to go down to minus 22. So this is 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I need to label 4, negative 12, negative 4, negative 12, and I need to label negative 3.5, negative 22. Which means that this graph looks like this. One part will go towards the asymptote. The other part needs to go either to positive infinity or negative infinity based on where your points are. But once you have those 2 points in your asymptote, you're going to be able to graph it completely. On an exam, graphing questions are worth at least 1 mark per transformation. So did you see that we did 4 transformations? On an exam, this would be a 4-mark, possibly a 5-mark question. Sometimes they give you an extra mark for the shape of the graph. Did you get the right shape of the graph? Because it wasn't given to you. Sometimes on exam questions and transformations, they say, here's a bunch of straight lines. Can you do these transformations? Then you get just a mark per transformation because they gave you the original shape. But if they don't give you the original shape, sometimes they give you an extra mark for that question.
On the exam, do they actually just give us transformation questions? Or would this give us these and go off of this knowledge that we know how to do transformations?
Bit of both, right? You could get a question that starts off like this, that says graph, and then it could be any parent function that we've done all year, right? So that includes exponentials now. We had square root graphs, x squared, x cubed, absolute value, 1 over x graphs, right? Those were our main parent ones from transformations. In sinusoidals, they could give you sine, cos, or tan, because we've done DAB-C for sine and cosine, and we have the parent graph of 10, we could move it left, right, up, and down, and do that as well. Okay? We're adding exponentials, which added in a whole bunch more, because they could give us any base. They can even give you bases that you've never seen before.
This is kind of a random question, but is it early dismissal for this?
No. It was the third Tuesday last week, wasn't it?
It's 3. I thought it was 2 Tuesdays.
Well, every first and third Tuesday is early dismissal in the afternoon. And now,
He's already 20
No,
something.
second and the,
I thought it was early.
so,
Me too.
yeah, we had it on the second,
I swear to God.
and.
let's see, let's hear it. We'll pull up a calendar here. Look at April. Look, we had first Tuesday was the second Tuesday the 9th, the 16th was the third Tuesday. April is a Tuesday nightmare because there's 5 Tuesdays and you only get early dismissal twice.
It should give us the fifth Tuesday.
The fifth Tuesday should just be holidays. Yeah, like,
Yeah.
let's
Same
be
with
serious.
29th of February. That should be
Like,
holiday.
really, that should
Gary, you should talk to the
definitely be
principal
holidays,
about that.
right?
Yeah.
I am going to introduce a new fun thing. We have holidays. Why not have holo-weeks or holo-months? Like holidays are just one day off, right? Imagine holo-weeks.
I feel like
Whole weeks
Christmas
off?
is like 3 days. Because you get Christmas Eve and Christmas, sometimes you get Boxing Day.
We should invent that. Holo years. Nobody works for a whole year. What would happen to our society? Probably fall apart. Okay, maybe not a good idea.
Nothing's
Okay.
changed.
So I think you have an empty page on 357. We are on page 357, going to graph something completely new with a number you maybe have never seen before. It is a famous number. How many people know the number E? And now you're like, Mr. JR, that is a letter. It's also a special number. It's on your calculator. There is an E button on your calculator. Push it, and up pops a number. See if you can find your E button. There's the first 10 digits of E. Have you seen that number before? No, it's a new number for you. It is special, just like pi. Pi is 3.14. How many people memorized for the free piece of pie this year?
I've got error.
You got an error on your E button? Oh, you didn't fill in a number. It's also right there. You could do it. So if you did it that way, you'd have to do E to the 1. And if you did it this way, you could just type in E. All right. So there's a new number. That's a crazy number. It goes on forever. It's actually easier to memorize than pi because it sure looks like it has a pattern. You see that 1828, 1828? That's just pure coincidence. After that, it doesn't follow that. It looks like it should keep going, right? But it doesn't. It just goes crazy after that. And so, what does this graph look like? Well, the same as every single other exponential graph. It's going to have y equals 0. It's going to have the point 0, 1. And it's going to have the point 1, e. Perfect. It increases just like any other one that is bigger than 1. It shouldn't be any harder to graph than normal. You could also graph y equals pi to the x. But e to the x is a super important graph for calculus. And the number e is super important for calculus. Yes.
Why?
Why? If you take any tangent line at any point, tangent line looks like this. Calculus is interested in the slopes of tangent lines. The slope of this one is 1. The slope at this one is e. It is the only function that exists where you pick any point and the slope of the tangent line is always identical to whatever the y-coordinate was. Throughout the whole graph. It's the only one that does that. And sure enough, if you check the point, comma, right, if I go up here at 2 comma e squared, and I draw a tangent line, the slope of that tangent line would be e squared. And it's the only graph that does that, which has huge implications in mathematics.
Do you know why it does that, or just that's why E is special?
That is why e is special. So what they found out is they were looking at different exponential functions, 2dx, 3dx, and the slopes were close, but not quite. So they're like, there has to be a number where it works, and it happens to be e.